And welcome back, students. As we continue our introduction to LC3, today we're going to discuss instruction processing. So let's just talk briefly about what instruction is. An instruction, for our purposes, is a fundamental unit of work. That means it's going to specify two things, an opcode and operands. An opcode is an operation to be performed, and then the operands is the data or locations that are going to be used for the operation. So think about this in terms of math, something you're a little more familiar with. It's like saying you have your operators and your operands. Operands, of course, are what's being manipulated, so like the numbers, and the operators would be like your symbols. So in this case, an instruction is encoded as a sequence of bits. So we're coming right back to using those bits of instruction. And often, but not always, these instructions have a fixed length, such as 16 or 32 bits. Control unit will then interpret instructions, so whatever your control unit is, depending on your architecture, will interpret that, and it's going to generate a sequence of control signals in order to carry out the operation. Now, the operation, once that has been determined, will be executed either completely or not at all. So if it's kind of like the back of that true-false thing, it determines if it can proceed. Now, a computer's instructions and their formats are known as its instruction set architecture, or RSA. You'll hear us talk about RSA a lot in this course. That's what it stands for. So let's just look at a little bit how instruction processing works. You can see we have this nice little flow chart here. It starts off with fetch instruction from memory, then decode instruction, then evaluate address, fetch operands from memory, execute operation, store result, and then returns back to the start and goes all over again. So here's a quick example with the LC3 of an add instruction. If you remember, the LC3 uses 16-bit instruction. So that means that those first 4 bits there, at position 15, 14, 13, and 12, are the thing that tells the program what kind of operation we're doing. In this case, this is an add. So what this does, it's going to add the contents of R2 to the contents of R6 and store the result in R6. So you can see in here, what you have is a breakdown. The first 4 bits are what kind of operation you're doing. In this case, this is an add operation. Then the next 3 bits determine the destination. Okay? This is the source. And then lastly, this is right down here, where you want that other source to go. So store the contents of R2. So this is R2 right here, source 1. To the contents of R6 it's going to R6. And then store the result in R6. So whatever your answer is, that's going to be source 2. Alright, as I mentioned, the LC3 has 16-bit instructions. Each instruction has a 4-bit opcode, that's bits 15 through 12. And the LC3 has 8 registers, R0 through R7 for temporary storage. Sources and destination of add are registers. So these registers right here, right, R0, R7, because with 3 bits, what's the maximum that you can get? Now this is an LDR instruction, all right, or a load instruction. This will read data from memory. Right? Now the base plus the offset mode, right, what that does is it adds the offset to the base register, and the result is the memory address. Load the memory address from destination register. So in this example, again, first 4 bits, that's our instruction. You can see here's our destination once more. So it says add the value 6 to the contents of R3, because if you look in here, this is R3, our base right here, and then to form a memory address. Load the contents of that memory location to R2. So this right here is R3. This is R2, a destination. Where is it being stored? And over here is, of course, that offset. Add the value of 6. So we look, that was, of course, our value of 6. Now, let's talk a little bit more about instruction processing. All right, and it follows this little thing, this flowchart here. So we're starting first with fetch. Alright, what this does is load the next instruction, add an address stored in the PC from memory into the instruction register, or the IR. It does that by copying contents of the PC into MAR, which then sends a read signal to memory, and it copies the contents of MDR into IDR. Then increment PC so it points the instruction in the sequence, and then PC becomes PC plus 1. Alright, from there, the next step is to decode. First, identify the opcode. In the LC3, this is always the first 4 bits of instruction. A 4 to 16 decoder inserts a control line corresponding to the desired opcode. Right now I'm just going to pause this as we kind of go through this. If you're a little confused about some of this instruction processing as I'm going through these slides, don't feel too overwhelmed about it. Right? Some of this is a little bit more above maybe what we'll go through, but it's information that you can have there so you can have a more fundamental understanding. Later on, as we start getting into things, you can look back at some of these things and say, oh, okay, now I have a better understanding of what that corresponds to. Right. So we're going back to the opcode. Remember, I showed you some examples with the add and the load. Here, that is using that opcode again. So depending on the opcode, we're going to identify other operands from the remaining bits. So for example, with LDR, the last 6 bits of that string of 16-bit is going to be your offset. For add, the last 3 bits is the source operand number 2. That's where we're storing our value. All right, then we're going to evaluate address. For instructions that require memory access, compute address used for access. So for examples, let's add the offset to the base register, such as LDR, add the offset to PC, or add offset to 0. Those are all different things that can happen. If we're looking at fetch operands, this obtains source operands needed to perform our operation. So some more examples: load data from memory, LDR, or we can read data from a register file using an add operation. Then we have execute. So this is going to then perform that operation using the source operands. So if we look at our examples here, we send those operands to the ALU, or the arithmetic logical unit, and assert an add signal. We could also do nothing. So this is used a lot for things like loads and saves. Then, lastly, we store the result. This writes the results to the destination, whether it's to the register or to memory. And some more examples again. The results of add is placed into the destination register. So if it was, for example, that source 2 we saw, if that was R2, then we are going to place that result in R2. The result of memory load is then placed in the destination register, and for store instruction, data is stored to memory. You write an address to MAR, data is to MDR, and then assert a write signal to memory. Alright, now let's talk a little bit about changing that sequence of instruction. In the fetch page, we increment the program counter by 1. So when we talk about PC, I'm not talking about personal computer. We're talking about program counter. Right. And just simply, program counter means, hey, you're starting this iteration at 0, and when we go through, we're adding 1 to it. Each time we go through it, we're adding 1. So after so many iterations, we're going to have to do something else. So what if we don't always want that instruction that follows this one? So examples are loops, if-thens, function calls. This is getting into a little bit more advanced concepts than what we may have talked about before, because, like I said, the program counter goes up to 1, and then it's going to go back to the top. All right, you will need, in order to do these sort of things like if-thens, special instruction that change the contents, of the PC. These are called control instructions. Now, jumps are unconditional. They always change the program counter. Branches are conditional. They change the program counter only if some condition is true. So, for example, the result of an add is 0. And here's an example of a jump instruction. And if you remember with jump instruction, remember, they always change the program counter. So, This is going to set the program counter to the value contained in the register. This becomes the address of the next instruction to fetch. So this is saying, rather than saying I'm going, 0, 1, 2, 3, 4, 5 with my program counter, if I want to say after I hit from 2, I want to jump to 5, I can use this command and have jump from like 2 to 5, depending upon whatever value is stored in that register. I guess I should also talk about this. You have your opcode right here. This is your jump right here. This is your base that it pulls it from. You notice the rest of these are simply just set to 0. Set to 0 because they don't need to have a stored value. So right in here, this is our base value. It gives us load the contents of R3 into the program counter. All right, and lastly, our instruction processing summary. Instructions in the end look just like data. It's all interpretation. So when we write our bits, when we start writing them, they just look like bits. I mean, how you have that bit constructed is going to look identical to one that's just data. They look at the first glance the same. It's how the program takes that data and looks at it that determines how the program can use it. Now, there are 3 basic kinds of instructions. We have computational instructions, so that's and add, things like that. We have data movement instructions like load and store. You have control instructions like jump. And there's also our 6 basic phases of instruction processing, which we talked about: FD, OP, EX, and S. That's the flow chart that we saw on the previous page. And of course, not all phases are needed by every instruction. And phases may take variable number of machine cycles. So, might take just 1 machine cycle, might take 20. And that concludes our notes for today, folks. Until next time.